Before the first light, before even time itself began to move, there was nothing. Or perhaps there was something, a silence, too perfect to measure. For centuries, scientists, philosophers, and dreamers have all asked the same impossible question. What happened before the Big Bang? Is there a beginning before the beginning, or is time itself only a trick of motion and memory? In this journey, we'll follow the faint traces left behind, radiation still whispering through space, the mathematics of invisible worlds, and the echoes of ancient light that may hold the memory of what came before everything we know. Because to understand how the universe began, we must first ask if it ever truly did. Before the first flicker of light, before the first particle ever collided with another, there was only silence. Not the silence of a room where sound has simply ceased, but a silence deeper than absence itself, a silence where even the idea of sound, or time, or direction had not yet been born. In that darkness, there were no colors, no warmth, no distance to measure, because nothing yet existed that could be measured. Physicists say that time began with the Big Bang, but if that is true, then what was this strange interval before time? Could there have been a before at all? Or does the question dissolve the moment it's asked, like a drop of ink in water that was never there to begin with? It is hard for the human mind to imagine a state without beginning, yet people have tried. For thousands of years, Aristotle, in the 4th century before Christ, argued that the universe must be eternal, with no true start or finish. To him, it was a grand motion without origin, like a wheel turning endlessly, its energy borrowed from its own perfection. Centuries later, St. Augustine of Hippo, writing in North Africa around the year 400, suggested something different. He wrote that time itself was part of creation, that God did not make the world in time, but made time along with the world. In his view, asking what came before creation was meaningless, because before could not exist where time had not yet begun. These thoughts, so ancient yet so precise, feel like the first tremors of curiosity reaching out toward the vast darkness we now call cosmology. And yet, millennia later, that same darkness still stands at the edge of everything we know. When Edwin Hubble looked through his telescope in 1929 and saw galaxies racing away from one another, the idea of a universe expanding from a single point began to take shape. The Big Bang became not just a theory, but the moment when existence itself ignited. Every atom, every spark of energy, every corner of the sky once fit inside something smaller than a grain of sand. Scientists call it a singularity, a word that means not just small, but undefined. It is the line at which equations break, where our laws of physics simply stop speaking. And beyond that line, there is only speculation. Imagine the universe at that edge. No space, no temperature, no ticking seconds. Just potential, heavy and waiting. If one could stand outside of it, though outside has no meaning here, it would feel less like looking at a place and more like listening for a sound that has not yet been invented. The entire cosmos was once compressed into that voiceless potential, and then something changed. We do not know what caused it. Some say it was a quantum fluctuation, the smallest possible tremor inside an endless field of possibility. Others speak of a prior universe collapsing and giving birth to ours like a heartbeat restarting after silence. Each theory is a language for describing something that cannot yet be seen. A whisper of meaning scratched into the surface of infinity. When modern scientists speak of before the Big Bang, they are forced to borrow words from time, before, after, beginning, moment. But these words collapse in on themselves when pushed far enough back. The Planck era, the first y, minus 43 seconds after the Big Bang, is as far as our equations can travel before they unravel. Beyond that, the laws that describe gravity and quantum mechanics no longer agree. It is as though reality itself refuses to be remembered past a certain point. The closer we get to zero, the less the universe allows us to speak. Still, curiosity pushes on. In quiet laboratories in places like Geneva, Pasadena, and Tokyo, men and women sit beside glowing screens, trying to recreate conditions that existed a fraction of a second after everything began. They build machines that smash particles together at almost the speed of light, hoping the fragments will tell them what the first instant looked like. And as they do, the same old questions rise again, not just scientific ones, but deeply human ones. What does it mean for something to come from nothing? Time had a start, will it have an end? And if the universe did emerge from emptiness, what was that emptiness made of? Perhaps the answer lies not in grand explosions, but in the quiet patterns of thought themselves. Every civilization, from the Maya to the Greeks to the monks of medieval Europe, has stood beneath the stars and wondered how it all began. Each story, each formula, each equation is an attempt to give shape to the silence. And maybe that is what makes the question so endless. The silence before time is not a thing to be solved. It is the canvas on which every discovery is drawn. In that darkness, before the first flash, before the universe even knew how to count a second, there was already the faintest pulse of curiosity, the same one that still beats inside us every time we look up and ask where it all began. In the beginning, there was a flash so bright that even now, after more than 13 billion years, its faint echo still hums quietly across the universe. It was not light as we understand it, not the kind that warms a face or glows through a window, but a blinding sea of energy that filled every direction at once. In that instant, the universe began to expand from something unimaginably small, denser than any star that would ever exist, into a rushing storm of heat and motion. Space itself stretched, time began to tick, and the first seconds were so violent that ordinary matter could not yet survive. What would one day become galaxies, stars, planets? And people was still only a cloud of particles colliding, scattering and reforming, as though creation itself were learning how to breathe. Physicists have tried to map those early moments in the same way a historian might try to record the first heartbeat of civilization. But everything happened too quickly to see directly. Within 1 second of that first flash, the temperature had already dropped enough for protons and neutrons to appear. Within 3 minutes, those tiny pieces fused to form the first atomic nuclei, mostly hydrogen and helium. The rest of the universe was still a burning fog of radiation so thick that light could not travel through it. For nearly 380,000 years, everything remained hidden inside that glowing mist, until the first atoms finally captured electrons, and light was at last free to move. That light never disappeared, spread, stretched, and cooled as the universe expanded, until it became what scientists now call the cosmic microwave background, the oldest photograph of existence. For centuries, no one knew it was there. Philosophers like Immanuel Kant in the 18th century imagined galaxies forming from clouds of gas. But the idea of the entire universe having a beginning still seemed too strange to accept. Even as late as the 1950s, many astronomers believed in the steady-state model, the thought that new matter constantly appeared as the universe expanded, keeping it eternal and unchanging. The Big Bang was still just a bold theory, something proposed by a quiet Belgian priest named Georges Lemaitre in 1931, who called it the primeval atom. Few took it seriously. There was no proof, no sound, no evidence left behind, or so it seemed. That changed one spring morning in 1964, when two engineers, Arno Penzias and Robert Wilson, began a series of routine maintenance checks on a large radio antenna in Holmdel, New Jersey. The horn-shaped dish was built for satellite communication experiments by Bell Laboratories. And their goal was simple: to eliminate all sources of noise that might interfere with their signal. Yet no matter what they tried, a faint hiss remained, a steady background hum that seemed to come from every direction. It was not from the nearby city of New York, nor from distant radio stations. It persisted during day and night, in summer and winter, and followed them through every frequency they tested. The noise was so stubborn that the two men began to suspect something mundane. They climbed inside the giant metal horn, brushed out the insulation, checked every cable, even found a family of pigeons nesting inside. Thinking the droppings might be the cause of the interference, they cleaned the dish carefully, chased the birds away, and repeated their measurements. But the signal did not vanish. The hiss continued, soft but unwavering, as if the universe itself were whispering through the static at the same time. Only 40 miles away at Princeton University, A group of physicists, led by Robert Dicke, was working on a design to detect exactly such a signal, the afterglow predicted by the Big Bang Theory. When Penzias and Wilson contacted them to describe the strange radiation, Dicke reportedly turned to his team and said, almost in disbelief, "Well, boys, we've been scooped." The two engineers had stumbled upon what every cosmologist had been searching for, the leftover light from the birth of the universe. When the discovery was announced later that year, it confirmed what Lemaître and others had long proposed. The faint microwave signal coming from all directions at a temperature of about 2.7 degrees above absolute zero was the cooled remnant of that first blinding flash. It was as though the universe had kept a record of its own creation, hidden in plain sight across the sky. Later missions, such as NASA's COBE satellite in 1989 and the Planck Observatory launched in 2009, would refine those measurements into detailed maps, showing tiny variations in temperature that would later become galaxies and clusters of stars. But in 1964, standing beside their quiet metal dish, Penzias and Wilson had unknowingly tuned in to the oldest sound in existence, a hiss that began before Earth, before the sun, before time itself as we know it. When we point radio telescopes toward the heavens today, that same whisper still fills the receivers. It is everywhere, between the stars, across the empty space. Even in the static of an old television set when no channel is tuned, every spark of that faint noise carries a fragment of the first moment stretched thin by billions of years. The universe, once a sea of blinding fire, now glows softly with its own memory. And as we listen, we are reminded that what began as a violent explosion of light has, across eternity, become a quiet hum, a faint, endless echo of the first flash that made everything possible. For most of human history, the night sky seemed like a still painting, cold and silent, a fixed backdrop for stories and calendars. Yet hidden behind that apparent stillness was the oldest light in existence, a dim and ancient whisper that began in the first moments of time itself. It is everywhere, in every direction, filling the universe evenly, like a faint fog of warmth that cannot be seen with the eyes, but can be felt through instruments built with patience and care. This light is the afterglow of creation, the same radiation that burst forth from the first flash and has been stretching and cooling for more than 13 billion years. Scientists call it the cosmic microwave background, and it became the key to understanding how everything, every star, planet, and living being came from a nearly invisible pattern etched across the early universe. In the late 1980s, a team of scientists and engineers gathered under the quiet hum of computers and cold metal walls at NASA's Goddard Space Flight Center to launch a mission that would change how we see the universe. The spacecraft was called COBE, short for Cosmic Background Explorer, and its job was not to look for stars or galaxies, but for the faint leftover heat from the Big Bang itself. When COBE was launched on November 18, 1989, aboard a Delta rocket from Vandenberg Air Force Base, it carried the hope of seeing back to a time when the universe was only a few 100,000 years old. No telescope on Earth could have done it, because our planet's atmosphere blocks most of the microwaves that carry those ancient signals. COBE drifted in orbit for 4 years, slowly scanning the sky, collecting data that came not in pictures, but in whispers, tiny changes in temperature measured to the thousandth of a degree. When the results were announced in 1992, the image they revealed was simple yet astonishing. An oval map of the sky covered in patches of red, blue, yellow, and green. Each color represented a difference in temperature, no greater than a few 100,000ths of a degree. These weren't random marks. They were the first structure ever seen in the early universe, the seeds of everything that would one day exist. The red areas showed slightly warmer, denser regions where gravity would pull matter together to form galaxies and clusters of stars. The blue areas were cooler, thinner regions where fewer galaxies would form. It was like looking at a baby picture of the universe, so faint, so quiet, and yet so filled with promise. Stephen Hawking, upon seeing the COBE results, called it the discovery of the century, if not of all time. A decade later, NASA launched another spacecraft, one even more sensitive and precise than COBE. It was called WMA Pitha-Wilkinson Microwave Anisotropy. Proband, it began its mission on June 30, 2001. WMAP orbited far from Earth. At a point known as L2, about 1.5 million kilometers away, where the pull of the Sun and Earth balanced each other perfectly. From there, it spent 9 years creating the most detailed map ever made of the cosmic background radiation. Each pixel in its final image represented a tiny piece of the sky, measured to a precision of millionths of a degree. What emerged was not chaos, but a quiet pattern. Faint unevenness that told scientists the universe was remarkably uniform, yet filled with delicate imperfections. Those imperfections were what allowed stars and galaxies to form, what made life itself possible. Without that subtle imbalance, the cosmos would have remained a smooth, empty fog forever. When WMAP's results were released in 2003, they revealed not just a map, but a timeline. Scientists could now tell the universe's exact age, 13.7 billion years. They could measure its composition, about 73% dark energy, 23% dark matter, and just 4% ordinary matter, the kind that makes up stars, planets, and people. That meant everything familiar, everything that shines or breathes. It's built from only a tiny fraction of what the universe contains. The rest remains hidden, silent, invisible. Yet shaping everything we see in 2009. A new chapter began when the European Space Agency launched the Planck satellite, named after the German physicist Max Planck, who had introduced the idea of energy quanta in 1900. Planck carried detectors, cooled to just 1/10 of a degree above absolute zero, allowing it to capture the softest possible signals without interference. For 4 years, it scanned the entire sky, tracing the cosmic microwave background with a clarity no instrument had achieved before. When its map was finally unveiled in 2013, it looked similar to the one from WMAP, but sharper and deeper, like comparing a watercolor to an oil painting. The fine mottled texture of hot and cold regions stretched across the cosmos like a cosmic fingerprint, showing that the pattern of creation was both random and ordered to balance. Between chance and law that shaped the path of everything that followed, these maps are not made of stars or dust, but of temperature and time. They are portraits of silence, the universe's memory of its own birth, carried not in words or light that can be seen, but in faint vibrations that linger everywhere. When astronomers look at those maps, they are not looking outward so much as backward, seeing a moment when the cosmos first learned to cool, to slow, to breathe. The ripples on those ancient images are the reason the Milky Way formed, the reason the sun burns, the reason human eyes evolved to see light at all. Every color, every wave, every pixel is part of the same story, that we are built from a pattern that was written before stars existed. Written in heat and silence, sometimes, when the observatories turn their antennas toward the sky and the data streams down in steady numbers. The sound of it is compared to static. But if one listens long enough, if one stretches imagination just slightly, it begins to sound like something else, not noise, but memory. The soft echo of the first light still breathing through the universe. In that silence lies the record of everything that ever was, waiting patiently, humming faintly, mapping the invisible with the calm persistence of eternity itself. When people look into the night sky, they often think of space as empty, a black expanse that stretches forever, filled with silence and nothing else. Yet the more closely scientists have studied that darkness, the more it has revealed itself to be alive in ways that defy our ordinary sense of stillness. What seems like nothing at all is in truth a restless ocean of energy, a field that never quite stops moving, even in its deepest calm. Physicists sometimes call this the quantum vacuum, or more poetically, the quantum foam. It is the idea that space, at its smallest scale, is not smooth and still, but frothing with invisible motion, particles appearing and vanishing in the blink of an eye, bubbles of possibility that flicker and collapse before anyone can measure them. It is not easy to picture such a thing, but one might imagine the surface of the sea under starlight, still from a distance, but endlessly trembling when seen up close. Each wave a brief pulse of something that will never quite be nothing. In the 1940s, a Dutch physicist named Hendrik Casimir found an unusual way to prove that this invisible hum was real. He predicted that if two metal plates were placed very close together, just a few micrometers apart, the empty space between them would press inward, as though the nothingness itself had weight. When this experiment was finally done, the plates really did attract each other. Not because of magnetism or static, but because of the vacuum's own energy. It was a discovery so strange that even today it feels more like a quiet magic than a piece of laboratory science. The idea that emptiness could push, modern scientists have gone even further, building laboratories that study this hum directly, in places like MIT, Caltech, and the Max Planck Institute in Munich. Researchers cool atoms to temperatures a fraction of a degree above absolute zero, a boundary so low that motion almost stops. In these chilled chambers, time itself seems to slow. Beams of laser light hold clouds of atoms in place, and sensors record their faint vibrations. It is here, in the coldest places humans have ever created, that we catch the smallest tremors of creation. Even when every bit of heat and motion is drained away, there remains a whisper, a background flicker that refuses to die. It is as if the universe itself cannot stop breathing, as if the void hums softly to remind us that it is not dead but dreaming. Some scientists describe this quiet motion as the universe's ground energy, a kind of heartbeat that runs beneath all matter and time. They calculate its effects through equations so delicate that a change in the 30th decimal place can alter an entire prediction. Yet beyond all the numbers lies something much simpler, the sense that even nothing is something. If the vacuum truly were empty, light could not travel through it, gravity could not bend it, the stars would not scatter their glow across it. The truth is that space is a medium, thin as thought, carrying the rhythm of creation itself. In 2011, at the National Institute of Standards and Technology in Boulder, Colorado, a group of physicists managed to cool a small cluster of rubidium atoms to just a few billionths of a degree above absolute zero. They trapped the atoms in a magnetic field so they floated, untouched by any surface. When they measured them, the atoms moved in patterns so faint they resembled waves made by invisible hands. What they were seeing, in their own quiet way, was the music of the vacuum energy that remained even after nearly everything else had been removed. Such experiments raise a question that has haunted both scientists and philosophers for centuries. Can nothing ever truly exist? When the ancient Greek thinker Democritus first proposed that everything was made of atoms moving through void, he imagined empty space as a pure absence, a background where things could happen, but that itself was completely blank. Now, more than 2,000 years later, that idea has become impossible to hold. The void is not blank. It seethes. It creates. It vibrates with the possibility of matter. The physicist John Wheeler, who worked alongside Einstein and coined the term black hole, once said that the vacuum was like a stage that could never be cleared. The lights might dim. The actors might leave, but the floorboards would still creak under unseen weight. When scientists listen to this hum, they are in a way listening to the universe remembering itself. The energy that fills empty space is thought to be the same energy that drove the expansion of the cosmos in its earliest moments, and perhaps the same force that continues to push galaxies apart today. It is called dark energy, though no one truly knows what it is. It does not glow or react. It cannot be bottled or touched, but it shapes everything. Every breath, every heartbeat, every drifting star exists because emptiness is not truly empty. If a person could somehow travel into the deepest void beyond stars, beyond galaxies, beyond the reach of light, they would not find stillness waiting for them. Even their atoms would flicker in and out. Fields would sway like grass in the wind, and faint ripples of radiation would move through the dark. Space would hum like the softest note of an endless song, and in that soundless vibration, one might begin to sense that nothingness is not an absence, but a secret fullness, the background that holds all beginnings. Perhaps that is why every attempt to define nothing fails. To exist is to change, and even change requires a place to happen. The void itself, by simply being, becomes something. What seems like silence turns out to be music too low for us to hear. The more we strip the universe down, cooling it, isolating it, emptying it, the more it reveals this faint shimmer of life. It is a reminder that the universe never truly stops. Not in stars, not in atoms, not even in the spaces between. Nothing, it seems, has never really existed. The void hums, the silence remembers, and the emptiness that surrounds us is simply creation. Resting between breaths, there are nights when the sky seems endless, when the stars scatter like sparks from a fire that never goes out, and it is in those moments that people have always wondered whether our universe is truly alone. The thought that all existence, every galaxy, every atom, every sound and silence could be contained within a single bubble of reality feels almost too small for the vastness that surrounds us. The more astronomers study the early universe, the more they suspect that what we call everything might be just one thread in a much larger tapestry, one bubble among countless others floating in an invisible sea of creation. This idea is known as the multiverse, a concept so strange and yet so beautiful that it blurs the line between science and dream. The story begins in the early 1980s. In a time when cosmologists were still trying to understand why the universe looked the way it did, the Big Bang Theory could explain how space expanded and cooled, but it left troubling questions. Why was the universe so uniform in every direction, as though its temperature and density had somehow balanced perfectly across unimaginable distances? And why did it seem to expand at just the right rate to avoid collapsing back into itself, or tearing apart too quickly? These puzzles lingered until a young Russian physicist named Andrei Lind began sketching an idea on napkins and scraps of paper in his Moscow apartment, an idea he would later call the inflationary universe. In simple terms, Lind proposed that in the first fraction of a second after the Big Bang, the universe underwent a burst of hyperfast expansion, growing exponentially in an instant. During that expansion, tiny fluctuations in the quantum fields, small waves of energy, were stretched to cosmic size, eventually becoming the seeds of galaxies and clusters of stars. But what made his idea even more daring was what came next. Lind realized that this inflation might not have stopped everywhere at once. Instead, it could continue in some regions of space while ending in others, like pockets of foam forming in a pot of boiling water. Each bubble would expand into its own universe, with its own laws of physics, its own constants, and perhaps even its own forms of matter and time. The process, he said, could go on forever. With new universes sprouting endlessly from the energy of the void, this notion called eternal inflation means that our universe, with its galaxies, stars, and laws of nature, may be just one bubble among an infinite number of others, each born from the same quiet sea of quantum energy. Some might have collapsed moments after forming, others might still be expanding beyond all reach. Some could be filled with light, others cold and dark, their stars made from particles that never existed here. There could be universes where gravity is weaker, where atoms never formed, where time moves differently, or perhaps where life developed in shapes and colors we cannot even imagine. And if this is true, then the Big Bang was not a beginning at all, but just a single ripple in a far greater ocean, a momentary breath in what might be called the universe that dreamed. The image of these endless bubbles is both haunting and strangely comforting. Scientists often illustrate it by comparing the cosmos to a vast foam, each bubble expanding separately, never touching, but always connected by the sea that birthed them. It suggests that creation is not a singular event, but a continuous unfolding, a chain of awakenings where one universe's silence becomes another's beginning. The equations that describe inflation predict that this process never truly ends. Even as some regions cool and slow down, others remain hot, energetic, and ready to give birth again. If we could somehow step outside our universe and look upon this cosmic foam, it might shimmer like the surface of a lake under moonlight, each ripple a reality, each spark a world. Andrei Lind, who fled the Soviet Union in the late 1980s and continued his work at Stanford University, often joked that the multiverse was an idea so vast that it made his own brain hurt. Yet he also spoke of it with wonder, as if the mathematics themselves were alive. He once described the universe as self-reproducing, a place where nature does not simply exist but keeps imagining itself into new forms. For him, the idea of infinite universes was not chaos, but an expression of creativity, the cosmos dreaming endlessly. Unaware of its own scale, many scientists remain cautious about the multiverse. Not because it lacks beauty, but because it may lie forever beyond measurement. No telescope can peer into another bubble. No signal can pass between worlds that expand faster than light can travel. And yet, even without proof, theory remains one of the most compelling answers to the oldest questions. Why does our universe look so perfectly tuned for life? And why is there something instead of nothing? If countless universes exist, each with different rules, then perhaps it is not surprising that we live in one that allows stars to burn and minds to ask questions. The others may be quiet, cold, and lifeless. Their stories unwritten, their skies forever dark. Sometimes, when astronomers study the faint radiation that fills the sky, or trace the patterns of galaxies across billions of light years, they pause to consider that what they see might only be a fraction of a greater reality. The night becomes heavier with mystery. The silence between stars begins to feel less like emptiness and more like the pause between. Breaths, a rhythm too large for human ears to hear. Maybe our universe is not alone, but dreaming among others. Each dream giving rise to another, each moment unfolding from the hum of something eternal. And perhaps, when we gaze upward, we are not looking into cold nothingness at all, but into the memory of a dream still forming, a dream that once thought itself alone and found that even the void could imagine, long before telescopes pointed into the cold distances of space. Before equations tried to measure the heartbeat of creation, humanity looked into the night and found stories instead of numbers. The sky was the first mystery, its darkness. The same quiet void that scientists now call precosmic was once seen as a living thing. To early civilizations, darkness was not empty, but full. A place of waiting, of unseen movement, of gods dreaming the world into being. Before light had a name, before stars were mapped or measured, there was only this shared silence between the earth and the heavens. A silence that human beings tried to fill with understanding. Every culture, separated by oceans and centuries, gazed upward and asked the same question. What was here before there was light? In ancient Egypt, along the banks of the Nile, priests and scribes spoke of none the boundless, formless water that existed before creation. It was not a sea as we know it, but an endless, deep, dark, and unmoving, from which all things would one day rise. Out of none came Adam, the first god, who stood on a small mound of dry land that surfaced like an island from the waters of eternity. With a breath or a word, depending on the version told, Adam began creation, separating the sky from the earth, bringing order from chaos. To the Egyptians, this was not just a myth, but a reflection of the river they lived beside. Each year the Nile flooded, covering the land in dark water and then receded, leaving behind fertile soil. The pattern of life and renewal became a cosmic symbol. The universe, like the river, was born from the flood of darkness, a cycle that never truly ended. Far to the east, in ancient India, the Rig Veda, the oldest known scripture, written perhaps around 1500 BCE, began with verses that still echo the same questions scientists ask today. There was neither existence nor non-existence, it says. There was neither the realm of space nor the sky, which is beyond. It describes the beginning as a cosmic ocean, endless and unbounded, stirred by a single breath of life that moved within it. This was not the act of a god separate from creation, but creation itself as a kind of awakening. The early Vedic poets did not see the universe as made from nothing but as born from something that slept within itself, a hum, a warmth, a potential. Their words spoke of desire as the first seed, thought as the first movement, and light as the first awakening of that desire into form. And then there is the story most familiar to the Western world. Found in the opening lines of Genesis, the earth was without form and void, and darkness was upon the face of the deep. The Hebrew text speaks of the Tiem, a deeper abyss over which the Spirit of God moved before saying, "Let there be light." The moment of speech and the moment of creation are the same, the void responding to vibration, the silence becoming sound. In its own poetic way, is not far from what cosmology would later describe, a universe beginning not from substance, but from expansion. From an event where light and matter burst into being from something indescribable. When read side by side, these ancient stories seem to be describing the same mystery in different languages. The Egyptians spoke of dark water, the Indians of a cosmic ocean, the Hebrews of an abyss. Each imagined the beginning as a place of silence and depth, where the boundaries between being and nothingness did not yet exist. Modern science speaks instead of singularities and inflation, but the spirit of the question is the same. Both the physicist and the priest are trying to name a time before time, to give shape to an emptiness that resists definition, whether through myth or mathematics. They are reaching toward the same invisible horizon the moment before light first. Learn to move? It is easy to forget how deeply ancient people observed the heavens, how patiently they watched the changing sky. Before cities drowned the stars in their artificial glow, the night was an open book. In the dry plateaus of Mesopotamia, in the deserts of Egypt, and on the high plains of the Andes, people carved the stories of creation into stone, mapping the cycles of light and darkness. They tracked the phases of the moon and the return of certain stars with the seasons. The first astronomers were also storytellers, blending observation and wonder into a single language. On the walls of tombs and clay tablets and temple carvings, they recorded their understanding of the universe not as cold data, but as living rhythm, the rise and fall of light, the death and rebirth of day. When archaeologists uncover those carvings now, when they find spirals etched into rock faces or rows of aligned stones marking solstices, they are reading the first cosmic scriptures. These were not written in letters, but in patterns, repetitions of circles, suns, and waves that mirrored the sky. To the people who made them, each mark carried meaning: the sun returning after winter, the stars shifting with the year, the divine order repeating itself. It was through these early acts of recording that humanity first began to bridge myth and measurement, turning awe into knowledge. The same impulse that drove a priest to describe the waters of none or a poet to imagine. The breath that stirred the void would one day drive scientists to build telescopes and detectors, to listen to the remnants of that first light even today. When satellites orbit the planet and scan the edges of the visible universe, we are doing what the ancient storytellers once did, looking for order in the dark. The instruments have changed, the language has grown more precise, but the wonder remains the same. We are still trying to imagine what existed before the first dawn, to describe a silence that no one has ever heard. The myths and the equations are both answers to the same question. What was the world before light had a name? Perhaps the truest answer lies not in what we discover, but in the act of asking itself in the gaze upward, in the carving of symbols and the whisper of stories shared beneath an unbroken sky. For in both science and myth, creation begins the same way, with curiosity rising out of the dark at the edge of the world, where the air burns your lungs with its purity and silence feels heavier than sound. A cluster of telescopes points into the oldest darkness known to humanity. The South Pole is one of the coldest and most isolated places on Earth, a plateau of endless white where temperatures can fall below -70 degrees Celsius, and even the wind seems to whisper more slowly. It is there, on that frozen continent, that scientists built a machine to look backward through time, not through history or human memory, but through the fabric of the cosmos itself. The BICEP experiment, short for background imaging of cosmic extragalactic polarization, began as a quiet effort in the early 2000s to study the faintest light in existence, the afterglow of the Big Bang. What makes Antarctica so perfect for this search is not just its cold, but its stillness. The air above the plateau holds almost no moisture, and moisture is the enemy of clarity when it comes to microwaves, the gentle waves of light left over from the birth of the universe. In more temperate places, water vapor distorts and absorbs these signals, smudging the ancient picture scientists are trying to read. But at the pole, there is nothing to interfere. No birds, no trees, no distant hum of machines. Only a pale horizon that never ends in a sky so sharp it feels like glass. The scientists who work there say that when you step outside the observatory at night, it is like standing in the middle of creation itself. No sound but the crunch of your boots. No smell, no motion. Only the slow rotation of stars above a land locked in eternal frost. The Biked telescope, installed in 2010, was built to study a specific signature in that ancient light, a delicate swirl called B-mode. Polarization, thought to be the fingerprint of gravitational waves left over from the universe's first instant of expansion. The idea behind this search reaches back to Andre Lin's theory of cosmic inflation, which proposed that the universe expanded faster than the speed of light for a fraction of a second after it began. If that happened, it would have sent ripples through space-time itself. Tiny waves that should still be visible today as faint twists in the cosmic microwave background. To find those patterns is to touch the echo of the universe's birth cry. To feel the pulse of creation still resonating after more than 13 billion years. Inside the Amundsen Scott South Pole Station, where the BICEP telescope is housed, scientists live like explorers on another planet. Supplies arrive only once a year, and during the long Antarctic winter, the sun vanishes for months, leaving the sky in permanent night. Instruments must be checked and calibrated in temperatures that can freeze skin in seconds. Yet for all the hardship, those who work there describe a kind of peace, a rhythm that comes from existing in a place so far removed from the noise of the rest of the world. Some compare it to standing on the edge of the known and listening for something older than time. When Bark 2 first released its results in March 2014, the world of cosmology held its breath. The team announced that they had found the signal, the faint, curling polarization patterns that matched what inflationary theory predicted. Headlines declared it the discovery of the century, the first evidence that the universe had truly inflated like a cosmic balloon in its first instant. Andre Lind himself was filmed in his California home when the news reached him, his face lighting with disbelief and joy. The quiet triumph of an idea first sketched in Soviet notebooks 3 decades earlier. For a brief moment, it seemed that humanity had looked all the way back to the beginning. But science, like the universe it studies, rarely moves in straight lines. As more data came in from the European Planck satellite, it became clear that much of the signal detected by BIPES 2 was likely caused not by ancient gravitational waves, but by cosmic dust within our own galaxy. Tiny particles of interstellar matter, aligned by magnetic fields, can mimic the same patterns in polarized light. What had seemed like the voice of creation might instead have been the whisper of our own cosmic neighborhood. It was a humbling moment, one that reminded everyone how icily the universe hides its secrets behind illusions of brilliance. Yet even that false start was not a failure. It proved that our instruments had reached the precision necessary to hear the difference between dust and eternity. Today, new experiments at the pole continue what BICEP began. Successors like BICEP 3 and the Keck Array refine their focus, peeling away layers of interference, trying again to isolate the true signal. Each observation adds a brushstroke to the faintest painting ever made, the map of everything that has ever existed, traced in light older than galaxies. Meanwhile, satellites orbiting high above Earth collect data that will be compared against what the telescopes on the ice record. The work is slow, meticulous, and endlessly patient. In this field, discovery is not a single moment of revelation, but a process of approaching truth, step by frozen step. Sometimes, when the scientists finish their night shift and step outside into the cold, they look up at the auroras curling across the sky and feel something that no datasheet can record. The shimmering lights above, the deep stillness below, the hum of equipment within the silent dome, all of it mirrors the early universe they are studying. Antarctica, they say, feels like the cosmos before it learned to speak. It is a place where the silence has weight, where light moves carefully, where time seems to hold its breath. And maybe that is why the answers to the oldest questions are being sought there. In the coldest frontier on Earth, because to understand how everything began, one must first learn to listen to the sound of nothing, and to find meaning in the quiet in physics. There is a peculiar kind of time travel that does not require a machine or a wormhole or even imagination, only mathematics. It is the act of taking the universe, with all its galaxies and gravity and energy, and running it backward through equations, tracing every motion and expansion toward an origin that none of us can see. The idea is simple in form, yet enormous in consequence. If the universe has been expanding since the Big Bang, then what happens if we reverse the direction of that expansion? Each galaxy would drift closer, each cluster would merge. The empty spaces between stars would shrink, and the cosmic background radiation would grow hotter and denser until, in theory, everything, all matter, energy, and space itself returns to a single point. Scientists call this a singularity, though that word feels too small for what it represents. It is a point without size, but not without meaning. A place where the laws of physics, as we know them, collapse. Where the universe forgets how to describe itself. The notion of rewinding time this way is not new, but it became truly profound in the 20th century. When the mathematics of general relativity gave the universe a kind of memory, Einstein's equations, completed in 1915, described how space and time bend around matter, creating what we call gravity. When applied to the cosmos as a whole, those equations predicted that the universe could not be static. It must either expand or contract. Einstein himself resisted the implication, adding what he called a cosmological constant to keep the universe still, a mathematical patch that he would later regret. But by the late 1920s, Edwin Hubble's telescope at Mount Wilson in California showed that distant galaxies were indeed moving away from us. Their light stretched to longer, redder wavelengths. The universe was expanding, and therefore it must once have been smaller. The equations, if run backward, pointed unavoidably toward a beginning. It was in the 1960s that two British scientists, Stephen Hawking and Roger Penrose, took this logic to its absolute limit. They were young men then, Hawking still a graduate student at Cambridge, Penrose working in London, and both fascinated by the strange geometry of space-time. Penrose, with his deep insight into mathematics, had already shown that black holes must contain singularities at their centers, points where gravity becomes infinite and time stops. Hawking extended the idea to the universe itself. If every particle, every planet, every star had once been compressed into a single region, then the universe must have begun in a singularity of its own, a place not just of infinite density but of no before. In 1970, their combined work demonstrated that general relativity, when applied honestly, could not avoid this conclusion. Time and space themselves had a beginning. And beyond that beginning, equations could not go. The realization carried an emotional weight that went far beyond mathematics. To imagine everything, the oceans, the cities, the stars, the memories of every living thing once contained in a single point smaller than an atom is almost unbearable. It suggests that separation is an illusion, that everything we know is still connected by the echo of that unity. Even the empty air between us carries atoms forged in stars that were born from the same primordial fire. Hawking once said that looking back toward the beginning of time was like trying to see past the horizon of the universe, an edge beyond which no information can reach us. Yet in that invisible boundary lies the story of everything that ever was or ever will be. Scientists who run these simulations speak about it almost reverently. On screens filled with colored graphs and grids, they reverse the expansion of galaxies. Watching clusters draw inward like tides retreating into a single ocean, the temperature rises, the density climbs, and the equations grow unstable, until the numbers themselves begin to overflow. Somewhere near 10 to the negative 43rd second, known as the Planck time, the universe becomes too dense, too energetic for any known theory to survive. Quantum mechanics and relativity, two pillars of modern science, refuse to speak the same language there. It is as though nature guards its own origin, allowing us to glimpse the trail of light, but never the spark that started it. For Hawking, who lived much of his life confined to a wheelchair, the singularity was not a limit, but a challenge. He once described his goal as nothing less than understanding the mind of God, by which he meant the fundamental order of the universe. Even as his body weakened, his equations reached deeper into that first instant, suggesting that time itself may have curled into a kind of closed loop that the universe could be finite but without boundaries, like the surface of a sphere that has no edge. In this model, there would be no need for a moment of creation. The universe would have no true beginning, just an eternal transition from one state to another, smooth and self-contained. It was a daring attempt to free science from the question of what came before. Yet it also carried a strange serenity, as if the cosmos itself were self-aware, unfolding and folding without end. Still, even the most elegant equations cannot erase the feeling that we are looking backward into something sacred. To rewind the universe is to undo ourselves, to trace not just matter, but meaning toward a single pulse of existence where all distinctions vanish. In that thought lies both awe and humility. Everything we see today, the light of distant galaxies, the warmth of the sun, the rhythm of a heartbeat, is part of a story that began in the same point. A moment that may never be fully understood yet continues to shape every second that follows. The cosmic rewind is not just a mathematical exercise. It is a mirror reminding us that every beginning hides within it the end, and every end quietly remembers the beginning. There is a moment so brief that it does not fit within our understanding of time, an instant so small that all known laws of physics collapse under its weight. Scientists call it the Planck time span, equal to about 1/10,000,000th of a trillionth of a second after the Big Bang. It is the smallest unit of time that has meaning in our current models of the universe and beyond it. Our equations can go no further. When we try to look before that, to speak of what might have happened earlier, the mathematics refuses to follow. The Planck time marks the edge of knowable history, the horizon beyond which everything, even logic, dissolves into silence. To understand why this limit exists, one must imagine rewinding the universe as scientists have tried to do, following galaxies backward until they merge into the early cosmic fire. As time contracts, temperatures rise, and densities climb to such unimaginable levels that matter and energy no longer behave as they do in the world we know. The fabric of space itself begins to ripple and twist like a storm-tossed ocean. In this regime, gravity, the great sculptor of planets and stars, becomes quantum, uncertain, unstable, fragmented. The equations of general relativity, which describe the grand movements of galaxies and black holes, can no longer agree with those of quantum mechanics, which govern the world of atoms and particles. It is as if the two most powerful languages ever devised by science begin speaking at once, but neither can understand the other. This moment, the Planck era, named after the German physicist Max Planck, who introduced the idea of natural limits in 1899, represents the boundary between comprehension and mystery. At times earlier than 10 seconds, the energies were so intense that our measurements lose meaning. Space and time cease to be smooth and continuous, and instead become foamy, granular, perhaps even chaotic. Some physicists imagine it as a kind of cosmic quantum storm where tiny fluctuations in energy bubbled and burst, creating miniature universes within universes, most of which vanished in an instant. Others see it as a blank curtain, a silence so pure that no cause or effect could yet exist. In either picture, what lies before that time remains forever hidden. Not because we lack courage to look, but because looking itself may be impossible in laboratories and observatories. Scientists continue to chase the faintest clues of that lost beginning. Experiments like those at CERN's Large Hadron Collider or the cosmic observatories scattered across Antarctica and Chile all seek the echoes of physics that ruled the Planck era. They recreate conditions a trillionth of a second after the Big Bang, but even that is an eternity away from the barrier. Each attempt brings us closer, yet also reminds us of how much remains unreachable. Theorists have written pages upon pages of equations trying to merge Einstein's relativity with quantum mechanics into a single theory of everything. Some call it string theory, a vision where every particle is a vibrating filament of energy, and where gravity might emerge from these hidden symmetries. Others turn to loop quantum gravity, imagining space-time as woven from tiny loops of geometry, like a cosmic fabric seen too closely to appear smooth. But so far, none of these approaches have broken through the silence of that first instant. There is a strange humility in realizing that science, for all its reach, still stops at that invisible wall. We can describe almost everything that has happened since then. From the first microseconds of the Big Bang, when quarks formed into protons and neutrons, to the birth of stars hundreds of millions of years later, to the slow cooling of the cosmos that continues even now. Yet that first fraction of a second remains a blank page, an unfinished sentence at the beginning of the book of existence. It is not that we have failed to write it, but that the ink itself does not yet exist. No experiment, no theory, no thought has been able to pierce the darkness of that moment that never was. For some, this boundary carries a kind of philosophical weight. It suggests that there may always be limits to what can be known, that perhaps mystery is built into the structure of reality. Even the greatest minds have approached it with reverence. Stephen Hawking once said that asking what happened before the Big Bang is like asking what lies north of the North Pole, a question that dissolves as soon as it is spoken. There was no before because time itself was born in that instant. The universe was not expanding into something. It was creating the very space and duration in which expansion could happen. It is a thought that bends the mind and quiets the heart, for it implies that everything, time, motion, causality is younger than a heartbeat. There is beauty in that silence. To stand at the limit of knowledge and know that beyond it lies something forever unspeakable is to feel both small and vast at once. Every star, every living thing, every thought that has ever been formed is the unfolding of that first moment. Yet the moment itself remains untouched, unreachable, pure. When scientists run their simulations backward, watching the universe shrink into fire and then into light and finally into equations, they are not merely calculating. They are praying in their own way, asking the cosmos to reveal what it has never shown. And when the equations fail, as they always do at 10 seconds, what remains is a kind of quiet acceptance that the universe keeps some of its secrets. It's not out of cruelty, but out of necessity. The moment before time began may never be described, yet it lingers in everything that followed. An invisible rhythm woven into the heartbeat of creation itself. There are moments in science when the world feels less like a machine and more like a song. When equations seem to hum beneath the surface of reality as if the universe itself were composed of rhythm and resonance. This feeling that everything we see might be the echo of something vibrating just beyond our perception lies at the heart of one of the most daring ideas in modern physics, the thought that the universe is not built from solid particles at all, but from tiny, invisible threads of energy that shimmer and vibrate in countless ways. It is called string theory, though the word string hardly captures the mystery it describes. In this view, the universe is not a static sculpture, but an endless symphony, each note giving rise to matter, light, and gravity. Every atom, every speck of dust, every breath of wind could be a different chord played by the same unseen instrument. The story of this hidden architecture began quietly in the 1970s, when physicists were struggling to unite the laws that governed the very large galaxies, stars and black holes, with the laws that ruled the very small atoms, electrons and quarks. Einstein's general relativity described gravity as the bending of spacetime, but it could not handle the strange, jittering behavior of quantum particles. Conversely, quantum mechanics explained the subatomic world, but broke apart when gravity was introduced. Each theory worked perfectly within its own domain, but refused to merge with the other. The dream of a theory of everything. One elegant framework that could describe all forces and particles seemed just out of reach. Then a few bold theorists began to imagine that the smallest things in the universe might not be points, as had always been assumed, but loops or strings. Their vibrations giving rise to the illusion of particles. A vibrating string can play many notes, and in the same way, these theoretical strings could produce different particles depending on how they moved. The electron, the photon, the quark each could be understood not as separate entities, but as different expressions of the same underlying string. In this model, reality becomes music written in dimensions we cannot see. To make the equations work, however, Physicists found that the universe needed more dimensions than the four we experience, not just up and down, left and right, forward and backward, and time, but perhaps 10 or 11 in total. Most of these extra dimensions, they proposed, are curled up so tightly that we will never notice them, like threads folded into the fabric of space itself. The notion was almost impossible to visualize, yet its mathematics produced harmony where none had existed before. As the theory evolved, new variations emerged. One of the most striking was brain cosmology, from the word membrane, which imagined our entire universe as a three-dimensional surface floating within a higher dimensional space. Just as pages can lie side by side in a closed book, each page its own world, the cosmos might contain countless brains existing parallel to ours. These brains might drift, collide, or brush against one another, each contact giving rise to phenomena that could look from within like a Big Bang. If that is true, then our universe could be just one page in an infinite library. Its birth, perhaps, is nothing more than the gentle touch of one world against another in a realm beyond sight. Physicists like Edward Witten, Leonard Susskind, and Brian Greene helped shape these ideas into the complex framework now known as M-theory, an attempt to unify all string theories under one banner. They described a universe that is fluid, multidimensional, and profoundly interconnected, where gravity and matter are not separate forces but reflections of deeper vibrations in the cosmic fabric. It is a vision that borders on the mystical, though it arises entirely from mathematics. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. And nowhere does that paradox feel stronger than here, where science begins to sound like philosophy and geometry begins to resemble poetry. Yet for all its beauty, string theory remains untested. Its scales are far beyond what any microscope or telescope can reach. The distances involved are so small, smaller than the Planck length, about 100 billion times smaller than an atom, that no experiment on Earth could ever probe them directly. Still, physicists search for hints, for shadows cast by the unseen architecture of reality. One of the most ambitious places to look is the Large Hadron Collider, or LHC, built near Geneva by the European Organization for Nuclear Research. Known as CERN, it is the largest and most powerful machine ever constructed. A circular tunnel, 27 kilometers long, buried beneath the French-Swiss border, where protons are accelerated too near the speed of light and smashed together in bursts of unimaginable energy. Inside that ring, detectors the size of cathedrals record the debris of these collisions, hoping to glimpse something that does not fit the standard model, perhaps. A particle that hints at extra dimensions or evidence of the tiny strings themselves. In 2012, the LHC made history by discovering the Higgs boson, the long-sought particle that gives mass to matter. It was a triumph for physics, confirming a key piece of the existing framework, yet for many, it was only a beginning. Since then, experiments have continued, pushing to higher energies, searching for patterns that might whisper of a deeper layer beneath the known. Some scientists hope to see the effects of supersymmetry, a prediction that every known particle has an unseen twin, an echo that could stabilize the equations of the universe. If such symmetry were found, it might be the first tangible hint of string theory's truth, a glimpse of the hidden architect's design. There is something humbling about the thought that all of existence might be woven from vibrations too small to see, that the universe could be one vast harmony echoing through unseen dimensions. Whether these theories will ever be proven may not matter as much as the wonder they inspire. They remind us that science is not only a search for facts, but also for meaning. That every equation is, in its own way, a question whispered into the dark. Perhaps, one day, we will find the evidence that ties these ideas to reality. Or perhaps they will remain like the faintest music in the background of the cosmos, a song that can be sensed but never heard, written by an architect who hides in the very structure of being itself, in the deep silence beyond Earth's atmosphere. Where sunlight fades into endless shadow, there drifts a golden mirror the size of a tennis court. A machine so precise that it can collect the faintest light ever to reach human eyes. The James Webb Space Telescope, launched on December 25, 2021. was built not simply to see farther than any telescope before it, but to look backward through time itself. Its vast honeycomb of mirrors, plated with gold so thin that a single flake could vanish between fingerprints, now floats nearly 1,000,000 miles from Earth at a place called Lagrange Point 2, where gravity from the Earth and Sun cancel in quiet balance. From that still vantage, Webb watches light that has been traveling for more than 13 billion years, light that began its journey when the first stars were newborn and galaxies were only beginning to form. Every night that its instruments open to the cosmos, Webb becomes something more than a telescope. It becomes a kind of memory machine, recording the earliest stories written in light. The principle is simple but staggering, because light moves at a finite speed. When we look far away, we are also looking back in time. The light from the moon takes a little over a second to reach us. From the sun, about 8 minutes, and from the nearest galaxy, more than 2 million years. The glow from the oldest galaxies Webb can see left its source billions of years before Earth even existed. In its mirrors, the past is still unfolding. The universe does not hide its history. It simply stretches it so thin that only a patient eye can find it again. When the telescope's first images were released to the public, on July 12, 2022, the world paused. Among them was one called the First Deep Field, a view that looked so small it could fit behind a grain of sand held at arm's length. And yet, inside that pinprick of darkness lay thousands of galaxies, each one home to billions of stars, each star a potential cradle for worlds. The image shimmered with color and depth, speckled with spirals, arcs, and faint smudges that were actually entire cosmic cities. Some of the light captured there had traveled for 13.1 billion years, crossing expanding space to fall onto a mirror shaped by human hands. It was as if the universe had taken a long breath and then, across time, whispered its earliest secrets into our machines. 2 scientists. The first Webb Deep Field was more than a photograph. It was a revelation. For decades, astronomers had used the Hubble Space Telescope to peer into the early universe, and its deep field images had already transformed our understanding of how galaxies grew. But Webb, with its infrared vision, could see beyond the reach of visible light, through dust and distance that had hidden the first generation of stars. These earliest stars were made only of hydrogen and helium, unpolluted by heavier elements forged later in stellar cores. They burned hotter and shorter than any that followed, and their light stretched and cooled as space expanded, shifting into infrared wavelengths that Webb was designed to detect. Looking through Webb's golden eyes, astronomers were not just seeing the early universe, they were witnessing the first sparks of structure emerging from chaos. The technology behind this vision is almost as poetic as the images themselves. Webb's primary mirror, composed of 18 hexagonal segments, had to be folded like an origami flower to fit into its rocket, then unfurled in space with perfect precision. Its instruments are cooled to near absolute zero by a sunshield the size of a house, layered 5 times to block the warmth of sunlight and earthlight. The faintest photon collected by its detectors can represent a journey longer than all of human history combined. And yet the machine performs its task in utter silence, floating in a temperature colder than -230 degrees Celsius, balanced between gravitational forces that hold it steady in a darkness no living thing has ever known. There is something deeply human about this act of looking backward. For all the machinery and mathematics, Webb's mission is also an act of memory, a way of asking where we came from by following the light that still remembers. When astronomers stare at those distant galaxies, they are not just studying physics. They are touching the edge of time, feeling the echo of creation's first expansion. Every photon that reaches the telescope carries within it a trace of its origin, the signature of a place and moment so distant that it exists now only as light. In a sense, the universe has been keeping a diary, and we have only just learned how to read it. Some have said that when Webb looks outward, the universe is looking inward through it. The same matter that formed the first stars eventually became the carbon in our breath and the iron in our blood. The same hydrogen that glows in those distant galaxies once roared in the cosmic dawn that birthed everything we are. To look back across billions of years is, in a strange way, to look into ourselves, to recognize that memory is not limited to minds, but is written into the structure of existence. Every atom carries a story of ancient fire. Every particle remembers its place in the first great unfolding. In the stillness of space, the Webb telescope waits, collecting these whispers from the beginning. Its gold mirrors do not blink. Its sensors do not sleep. And yet what it gathers is not cold data alone, but something like remembrance. The universe, vast and expanding, seems to be recalling its own childhood through this silent instrument, as though it were dreaming of the moment it first began to shine. And down on Earth, when those images appear on screens in darkened control rooms or across living rooms full of wonder, it feels for a brief moment as if we too remember, not with our minds, but with the particles that once burned in the same star's web now sees across time. Still glowing in the deep field of eternity, there is a peculiar kind of silence that falls in both a laboratory and a monastery, a silence that hums not with emptiness, but with expectancy. In both places, whether it is the dim chapel where a monk kneels in prayer, or the underground tunnel of CERN, where physicists monitor streams of data from colliding protons, the human spirit reaches outward, toward something vast and unseen. The setting may differ, one filled with the scent of candles and stone, the other with steel and magnetic coils colder than outer space, but the gesture is the same, quiet stretching of the mind toward mystery. Both the scientist and the monk live in service to questions that have no easy answers, and both learn that true discovery, whether of God or of nature, begins in stillness at the European Organization for Nuclear Research, known as CERN, near Geneva, Switzerland. The search for what would later be called the God particle took decades of collective patience. Deep beneath the border between France and Switzerland, a ring of tunnels stretches for 27 kilometers, forming the Large Hadron Collider, the most powerful scientific instrument ever built. Inside, beams of protons are accelerated to nearly the speed of light, guided by superconducting magnets chilled to -271 degrees Celsius. When those beams collide, they produce showers of subatomic debris that last for less than a trillionth of a second. A flicker of creation recreated in miniature. The goal was not spectacle, but understanding, to find the mechanism that gives matter its mass, to reveal one of the final missing pieces in the great puzzle of physics known as the Standard Model. In July 2012, after years of searching, the scientists at CERN announced that they had found it, the Higgs boson, a particle predicted nearly half a century earlier by British physicist Peter Higgs and others. It was the invisible key that explained why some particles had weight while others did not, why the universe did not remain a cloud of light after the Big Bang, but instead formed stars, planets, and bodies that could hold together. The discovery confirmed that there exists a field permeating all of space, the Higgs field, and that every particle passing through it acquires mass. Much as a swimmer feels resistance moving through water, without it, nothing solid would exist. There would be no matter, no structure, no world to wonder about. When journalists heard the news, they needed a name that would speak beyond equations, something ordinary people could grasp. They called it the God particle, borrowing the phrase from a book written by physicist Leon Lederman, who had used the term half-jokingly to express both the particle's importance and the frustration of finding it. Scientists themselves disliked the label, insisting it had nothing to do with theology. Yet the phrase endured because it captured something more poetic, the sense that beneath all things lies a single principle, unseen yet sustaining, that connects the smallest with the infinite. For a brief moment, physics and faith seemed to share the same breath. Peter Higgs, a modest man who avoided public attention, wept quietly when he saw the announcement. The discovery had taken 48 years to confirm, and he was 83 when it came. His colleagues in the auditorium erupted in applause, but he sat in silence, overwhelmed not by triumph, but by the immensity of what it meant. The equations he had written on paper in 1964 were now inscribed in the structure of reality itself. In that moment, science and humility became indistinguishable. He later said that he had never imagined he would live to see it proven, and that the true beauty of the discovery was not in the fame it brought, but in the order it revealed. A whisper of coherence in a universe that might otherwise seem chaotic in monasteries. That same whisper is sought in a different way. The monk sits in quiet meditation or chants the same line of scripture until it dissolves into rhythm. Not searching for mass or energy, but for presence, for the faint trace of meaning in the stillness between breaths. The tools are not machines but rituals, words repeated until they lose their edges and become pure sound. And yet, when the monk opens his eyes and the physicist looks into a detector screen, both are staring into the unknown. Both encounter the same mixture of awe and limitation. The knowledge that no matter how far we reach, the mystery will always stretch farther. The physicist speaks in numbers, the monk in prayers. But both are humbled by the same realization, that what we call truth lies beyond the reach of certainty. The discovery of the Higgs boson did not end the story of physics any more than a revelation ends faith. It opened new questions about dark matter, dark energy, and the invisible architecture that holds galaxies in place. It reminded scientists that even when they find what they are looking for, the horizon simply moves. The universe does not yield its secrets easily. It invites pursuit, and in that pursuit there is devotion. The silence of the collider, broken only by the whir of cooling systems and the faint hum of magnets, is not unlike the silence of a cloister before dawn. Both are filled with unseen motion, with the pulse of something vast moving just beyond comprehension. Perhaps that is why, despite the precision of their instruments, scientists often describe their work with the language of wonder. They speak of elegance, beauty, simplicity, words that belong as much to cathedrals as to laboratories. The Higgs boson was never about proving the divine. Yet in its discovery, there was a shared feeling of reverence, a sense that the universe, in all its complexity, is more than random. It is something ordered, mysterious, and astonishing, capable of stirring both calculation and prayer. When the lights dim at CERN and the night shift takes over, the massive ring continues to hum beneath the earth, circling endlessly like a mantra repeated in metal and magnetism. Above ground, the Alps lie silent under the stars, their peaks catching the faint glow of distant galaxies. Somewhere in those galaxies, light from the earliest times still travels, carrying with it the same laws that govern the particles below. The world remains vast, unknowable, and sacred in its own way. And whether one stands in a chapel or a laboratory, the act of seeking, of listening into that infinite silence is the same. For at the edge of knowledge and faith alike, there is always a pause, a breath, and the quiet understanding that to reach toward the unknown is, perhaps, the most human prayer of all. In the quiet corners of cosmology, where mathematics begins to resemble meditation, there lingers an idea both ancient and newly reborn. The thought that the universe may not have a single beginning or an ultimate end, but rather a rhythm, a pulse, an eternal return. It is a vision in which everything that exists is part of a vast cycle, expanding and collapsing like the slow breath of some cosmic being. This theory, known among scientists as the Big Crunch, suggests that the universe, which began with a furious explosion of energy, might one day reverse its motion and fall back in upon itself. The galaxies drawing closer, the stars burning out, space folding tighter and tighter until all that remains is the same singular point from which it began. From there, perhaps it would ignite again a new Big Bang. A new age of light, the heartbeat of creation restarting once more. The idea sounds modern, born of telescopes and supercomputers. But in truth it echoes stories told thousands of years before the word cosmos was ever written. The ancient Hindus imagined time not as a straight line, but as an endless wheel, turning through vast epochs called yugas, each lasting millions of years. In their vision, the universe is created, sustained, destroyed in repeating cycles, each one a breath of Brahma, the great cosmic being. One exhalation brings light and life. One inhalation returns everything to silence. Between the two lies eternity. The Mayans, too, spoke of the world as something born, ended, and reborn again. their calendars tracing cycles of renewal rather than finality. They saw time as sacred, not because it promised permanence, but because it promised return. What was lost would rise again. What died would awaken. For them, the universe was not a machine ticking toward an end, but a story retold endlessly, its characters reborn in new forms with each turning of the wheel. In the 20th century, long after myth had given way to mathematics, scientists began to glimpse the same pattern through the lens of observation. Edwin Hubble's discovery in 1929 that galaxies were racing away from one another proved that the universe was expanding. But it also raised a deeper question. Would that expansion continue forever? Or would gravity, the invisible hand holding everything together, one day pull it all back? For decades, physicists debated the balance between expansion and collapse. If the density of matter and energy in the cosmos was high enough, gravity might eventually slow the expansion to a stop and then reverse it, drawing every atom back toward the center. In that final act, galaxies would merge, stars would ignite and die, and the fabric of space itself would shrink until time could no longer distinguish before from after. The Big Crunch would be not just an end, but a beginning, a mirror of the Big Bang. In the 1970s and 1980s, as cosmologists refined their equations, some began to see beauty in the idea of an oscillating universe, one that expands, collapses, and expands again in an endless sequence of cosmic cycles. Each Big Bang would follow a Big Crunch, each universe giving birth to another, like a phoenix rising from its own ashes. The British mathematician and physicist Richard Tolman had proposed such a model as early as 1934, suggesting that entropy, the measure of disorder in the universe, might reset after each collapse, allowing the cycle to begin anew. Later theories influenced by quantum mechanics and the discovery of cosmic inflation revived this vision under different names: cyclic cosmology, ekpyrotic theory, or simply the eternal universe. Each one whispered of repetition, the same grand story told again and again, with only slight variations in the details. To imagine such a future is to picture a slow and solemn reversal of everything we know. Billions of years from now, as dark energy weakens or changes its nature, the outward flight of galaxies could begin to falter. The great clusters would slow, their light dimming, until gravity's pull turned them inward. The night sky would begin to grow brighter again, not with new stars, but with old ones drifting back together, their collisions setting the heavens aflame. Over unimaginable ages, the distances between galaxies would vanish. The universe would grow hotter, denser, and smaller, until the fabric of space itself began to fold. In the final instant, all matter would melt into pure energy. Time would compress into a single heartbeat, and the universe would return to the state from which it first emerged, a luminous, infinite point containing all that ever was and ever would be. Some cosmologists, like Paul Steinhardt and Neil Turok in the early 2000s, reimagined this process in the language of modern physics. In their brain model, inspired by string theory, our universe is one of many, existing as a membrane within higher dimensional space. They proposed that the Big Bang might not have been the absolute beginning, but the result of two such brains colliding, a cosmic rebound that could happen again and again. Each collision would create a new universe with new laws and new matter, while the deeper reality, the greater cosmos beyond, would continue undisturbed. In this way, the idea of the Big Crunch merges with that of eternal renewal. Destruction and creation are not opposites, but partners in the same endless dance. There is something hauntingly familiar about this rhythm. It feels less like physics and more like memory, as if the universe itself remembers what it was and returns to it out of instinct. Perhaps that is why the notion of a cyclic cosmos resonates so deeply, not just with scientists, but with poets, philosophers, and seekers of every kind. It restores to the universe a kind of breathing, a pulse that mirrors our own. Even if the end comes as a collapse, it is not a final silence, but a pause between inhalations. The stars that fade will shine again. The atoms that fall apart will reassemble. The story will be told anew in a slightly different tongue. And if this is true, if the universe expands and collapses forever, if time itself is circular, then perhaps the Big Bang was not the first moment, and the Big Crunch will not be the last. Perhaps the cosmos, like the ancient myths once said, has always been alive, dreaming, and awakening. Dying and being born again, an infinite rhythm, where every ending hides within it the promise of another dawn. In that vision, the universe is not a line drawn through time, but a circle without edges. And we, the fleeting observers, are simply the witnesses of one beat in its eternal heart. In a quiet laboratory somewhere in the mountains of Colorado, inside a room filled with the faint hum of cooling systems and the soft pulse of lasers, a group of scientists has done something extraordinary. They have trapped time itself, or at least slowed it enough to see it behave differently from what human experience suggests it should. They work at the National Institute of Standards and Technology, where the world's most accurate atomic clocks reside. These are not clocks in any ordinary sense. They have no hands, no ticking gears, no sound at all. Instead, they measure the rhythm of atoms, the vibrations of strontium or ytterbium cooled to nearly absolute zero, oscillating with a precision so fine that if one of these clocks were to run for the entire age of the universe, it would lose less than a second. It is here, in this silence of light and cold, that scientists have begun to test the limits of now, stretching the concept of the present until it trembles under scrutiny. The idea of measuring time through atoms began in the mid-20th century, when physicists discovered that the vibrations of certain elements were far more consistent than any mechanical system. Cesium-133, for instance, was chosen in 1967 as the standard for defining the second, exactly 9,192,631,770 oscillations of its radiation frequency. But as technology improved, the ambition grew. The atomic clocks of today no longer rely on cesium, but on optical transitions within atoms that vibrate at even higher frequencies. Allowing for measurements 100 times more precise, these devices sit in temperature-controlled rooms, isolated from sound, shielded from magnetic interference, and bathed in laser light tuned so exactly that it seems less like illumination and more like music. Each pulse marks the passage of time with a steadiness that no human perception can match. What these experiments have revealed is something both expected and disquieting: that time, that most fundamental of experiences, does not flow evenly everywhere. In 2010, researchers using a pair of aluminum-ion clocks separated vertically by less than a foot were able to detect a difference in their ticking due to gravity. The one closer to the ground, pulled ever so slightly harder by the Earth's mass, ran just a tiny bit slower than the one above. The difference was so small, it could only be measured in trillionths of a second. Yet it confirmed a truth first predicted by Einstein a century earlier. Gravity bends not only space but time itself. The stronger the pull of gravity, the slower the passage of moments. A clock on a mountain ticks a little faster than a clock by the sea. And a person living at the top of a skyscraper ages infinitesimally quicker than one at its base. Though no one could ever feel it, this realization stretches the mind in quiet ways. The notion that time, the thing we measure our lives by, can stretch and shrink depending on where we stand, seems almost spiritual in its implications. In the laboratories where these measurements are taken, the scientists speak in numbers and data, yet what they are truly doing is touching the structure of reality. Every refinement in precision brings them closer to a mystery that time may not be a single, universal river, but a collection of countless small streams, each flowing at its own rate through the landscape of the cosmos. In space, where gravity varies wildly from star to star and from planet to planet, those streams twist and warp like currents in a restless ocean. For astronauts aboard satellites orbiting Earth, clocks tick ever so slightly faster than those on the ground, and corrections must be made constantly to ensure that systems like GPS remain accurate. Even navigation, it turns out, depends on understanding how the universe folds time. The colder the experiments become, the stranger the results appear. At near absolute zero, where atoms almost stop moving, scientists observe behavior that seems to blur the boundary between time and stillness. In cryogenic tests, particles enter states where they move as one. Perfectly synchronized, their oscillations forming a kind of frozen rhythm that defies the ordinary flow of seconds. It is as though by stripping away heat, the energy of motion and disorder, the experimenters are revealing an underlying calm that has always been there, hidden beneath the rush of ordinary experience. At these temperatures, time feels less like a forward march and more like a quiet vibration, a hum that simply exists. Some physicists have even speculated that time itself may emerge from such quantum vibrations, not as a background against which events occur, but as the product of the events themselves, a rhythm born from motion, not the stage upon which motion unfolds. And yet, for all their precision, these clocks do not capture what time feels like: its weight, its movement, its passing presence in a heartbeat or a memory. They can measure differences so small, they border on nothingness. But they cannot explain why time should exist at all, or why we sense it as flowing. The deeper scientists look, the more elusive it becomes, as if time, aware of their pursuit, retreats into subtler forms. Einstein once remarked that the distinction between past, present, and future is only a stubbornly persistent illusion. And perhaps these atomic clocks are the instruments revealing that illusion in slow motion. They show that now is not universal, that even this word, this breath, exists differently for each observer, each atom, each corner of the cosmos, in this way. The laboratories where time is measured have become places of quiet wonder, almost monasteries of modern thought. The researchers who tend these machines, adjusting lasers and calibrating frequencies, are not so different from monks keeping vigil through the night, watching the seconds drift like stars. Each improvement, each decimal of precision, is a way of listening more closely to the heartbeat of the universe. And the more carefully they listen, the more mysterious the rhythm becomes. Somewhere between the frozen atoms and the bending of light, between the ticking of the clock and the silence that surrounds it, time reveals itself as both utterly real and completely unknowable, a thing we can measure but never hold, a truth we can name but never fully understand. It is the one constant that refuses to stay still, and the deeper we chase it, the more it slips through our fingers, leaving only the faintest echo of motion, a hum at the edge of silence that reminds us that even in stillness, the universe is never at rest. There are places in the universe where the known laws of nature come undone, where light itself falters and time forgets how to move forward. These places are black holes, the silent borders of reality, the regions where gravity becomes so absolute that even the concept of escape ceases to have meaning. To imagine one is to imagine the edge of the possible, a place where space folds in on itself and what was once open becomes sealed. They are not empty holes, as their name might suggest, but dense remnants of collapsed stars, so compressed that a mountain's worth of matter could fit into something smaller than a grain of sand. Around them the universe bends, curving space and time into shapes so extreme that the path of light becomes a spiral, circling endlessly before it disappears. They are the graves of stars, and perhaps the wombs of something older, the surface of a black hole, invisible yet absolute, is called the event horizon, the point at which not even light, the fastest thing in existence, can outrun the gravitational pull. To an outside observer, anything crossing this line appears to freeze, stretched thinner and thinner by the distortion of time. If you were to watch an object fall toward a black hole, you would never see it cross. Its light would slow and redden until it faded completely, as if the universe itself were refusing to show you what comes next. Inside that border, the rules of physics we understand stop working. The equations that describe gravity, energy, and motion collapse into infinities. Like a sentence that cannot be finished because the language itself runs out of words, for decades, scientists treated black holes as cosmic dead ends, regions where matter and information went to die. Yet one man refused to accept that the story ended there. In the 1970s, Stephen Hawking, working at Cambridge University, began to think about what happens at the very edge of a black hole. where quantum mechanics, the physics of the very small, must collide with general relativity, the physics of the very large. His insight was that space around the event horizon is not empty, but seething with virtual particles that appear and vanish in pairs. Occasionally, one of these pairs becomes separated. One particle falls into the hole while the other escapes, stealing a fragment of the black hole's energy in the process. This slow leakage, now known as Hawking radiation, implies that black holes are not eternal. Over unimaginable stretches of time, they can evaporate, shrinking until they vanish completely, leaving behind not darkness, but an unanswered question. That question haunted Hawking and every physicist who came after him. What happens to the information about everything that falls into a black hole? According to quantum theory, information can never be destroyed. It may be transformed or hidden, but it cannot simply vanish. Yet, if a black hole evaporates and all that remains is faint radiation, where does the information go? This became known as the black hole information paradox, and it stands as one of the deepest puzzles in modern science. For if information truly disappears, then the entire framework of quantum mechanics would crumble. With it, our understanding of the universe's most basic order. But if the information remains, it must be stored somewhere. Perhaps woven into the fabric of the event horizon itself, a cosmic ledger written on the border of being and nothingness. Some scientists have suggested that the horizon acts like a kind of hologram, encoding everything that has ever crossed it in an unimaginably complex pattern of energy. Leonard Susskind and Gerard T. Hooft were among the first to explore this idea in the 1990s, proposing what became known as the holographic principle, the notion that all the information contained within a region of space might be represented on its surface, as if reality itself were a projection from a deeper dimension. In that view, black holes are not endings, but archives, preserving the memory of everything that ever touched them. The faint radiation they emit could then be seen as a slow whisper of those memories returning to the universe. Scattered like ashes into the cosmic wind, to stand at the edge of this understanding is to glimpse something profoundly humbling. Black holes, once thought to be pure destruction, might instead be keepers of history. Some physicists have gone even further, suggesting that they could contain the seeds of new universes within them, that when matter collapses into a singularity, it may trigger the birth of another cosmos, expanding in a dimension we cannot perceive. In that sense, every black hole could be a bridge, a portal through which reality renews itself. The idea is speculative, but it carries a quiet symmetry, just as the Big Bang may have arisen from a state of infinite density. Perhaps that density exists still within these silent maws scattered across the sky, each one carrying a memory of what came before. If universes can be born from collapse, then creation and destruction are not opposites, but partners, forever trading roles in the same endless story. When astronomers look at images of black holes like the first one captured by the Event Horizon Telescope in 2019, showing a glowing ring of light surrounding a dark core in the galaxy M87, they are not merely seeing an object, but a moment of infinite tension between presence and absence. The light around it bends and circles, showing the path of matter as it falls into silence. Inside, time stretches so far that it may as well have stopped. For the particles trapped there, a second could last forever. For the universe outside, eternity might pass in an instant. These are not contradictions, but reminders that reality is not uniform. Time and existence bend differently depending on where one stands. And at the border of a black hole, that difference becomes everything. To think of black holes as portals rather than prisons is to restore wonder to the universe. They are reminders that the cosmos is not done with mystery, that even in its darkest regions, something continues, an echo of light, a whisper of memory, a possibility of rebirth. If they do store the information of all that falls within, then each black hole is a kind of cosmic mind, holding the history of stars, planets, and lives long vanished, perhaps in some unimaginable future, when all light has faded and all matter has dissolved. The last traces of our universe will remain inside these quiet sentinels, waiting to be released again. And in that release, in that return, the universe will remember itself, as it always has. By falling into darkness and then learning once more how to shine, everything that lives is, in a quiet way, a memory. The air that moves through the lungs, the blood that runs beneath the skin, even the atoms that make up the bones, are not new things, but ancient ones. They have belonged to other bodies, other stars, other times. When we breathe, the hydrogen in our breath is the same that once burned in the cores of the earliest suns. Those first great fires that illuminated the dark after the universe was born. Every element in the human body is a kind of inheritance, passed down not through families or generations, but through the entire history of existence. We are not made of something separate from the cosmos. We are the cosmos, briefly awake. The story begins long before Earth had oceans or air. When the universe was still young and wild, after the Big Bang, only the simplest elements existed: hydrogen and helium, with just a trace of lithium. They were the raw ingredients of everything, and for hundreds of millions of years they drifted in the cooling dark until gravity gathered them into clouds, and then into the first stars. Those stars were enormous, far greater than any that now burn in our skies, and their lives were short and fierce. Inside their cores, fusion raged, transforming the lightest elements into heavier ones: carbon, oxygen, nitrogen, iron, the building blocks of worlds and of life itself. When these stars grew old, their fuel exhausted, they died in explosions so vast that for a moment they outshone entire galaxies. In those deaths, they cast their newly forged elements into space, scattering the materials of future planets like seeds. Astronomers can still trace this process in the starlight that reaches Earth today. They see the fingerprints of these ancient forges in the patterns of light emitted by distant suns, each line revealing which elements were born in its heart. The calcium in a person's bones was once part of a star that lived and died long before the sun existed. The iron in blood, the oxygen in breath, the carbon in every cell, all of it formed in stellar furnaces billions of years ago. The poet and the scientist calls this star stuff, a phrase made famous by Carl Sagan. It reminded us that we are the universe looking back at itself. The atoms that make up a person are old beyond imagining. Older than the earth, older than any living thing that has ever stirred. To look in a mirror is to see starlight shaped into memory. When Earth finally condensed from the debris of those earlier stars, it's about 4.5 billion years ago, the materials that had once drifted freely in space found themselves bound together in a new form. Dust became rock, rock became ocean, ocean gave rise to life. Through endless cycles of heat and pressure, these same atoms were borrowed and returned, moving through volcanoes and rivers, through fish and trees, through everything that ever lived. The hydrogen that fills the cells of the human body today may once have moved through a whale, or a fern, or a comet that fell into a prehistoric sea. The oxygen we breathe was once part of ice on a moon or vapor in a nebula. Even the simplest act of inhalation is a communion with history, the universe, entering and leaving itself. DNA, quiet spiral that holds the code of life, is another kind of memory written in matter. Its molecules built from carbon, hydrogen, oxygen, and nitrogen trace their ancestry to stars that burned and died billions of years before the first cell divided. Inside every human being, in the double helix of every cell, is a record of the same cosmic story: hydrogen, older than galaxies; carbon shaped by ancient fusion, oxygen born in stellar fire. The human genome, with its long, winding code of repetition and variation, might be seen as the universe continuing its experiment in complexity. It remembers not only biological ancestry, but chemical ancestry, the long continuity between dust and consciousness. When scientists analyze meteorites, they find amino acids in organic molecules older than Earth, suggesting that the seeds of life's chemistry were already scattered through the cosmos before the planet even formed. This idea, known as panspermia, does not reduce life's wonder, but expands it. It implies that life is not a rare accident, but a natural expression of the universe, that wherever matter gathers and cools, memory takes root and something begins to awaken. Perhaps intelligence, emotion, even the capacity for awe are not human inventions, but echoes of that original self-awareness that flickered in the first stars. The atoms that once belonged to those early fires now think and feel, write and remember, forming sentences about the very cosmos that made them. When we look at the night sky, it is easy to feel small, but the truth is stranger and more intimate. The stars we see are not far away in spirit, for they are the ancestors of our own atoms. The hydrogen burning in their cores is the same that burns more quietly in the mitochondria of our cells, driving the chemical reactions that keep us alive. The light that reaches our eyes traveled through the same space our matter once occupied, billions of years ago, before gravity drew it together into this brief, breathing form. To feel warmth, to think, to love, these are ways the universe remembers its own heat, its own unfolding. Every human being is thus a record of what came before, not through words or fossils, but through substance. The body is an archive written in elements, its sentences made of starlight and dust, its punctuation marked by breath. Even after death, those atoms will scatter again, returning to the soil, the air, the water, and eventually, perhaps, 2 stars yet unborn. The cycle is endless. What was once part of the first fire will one day burn again. Nothing is truly lost, only changed, passed forward, carried in new forms. The universe is not a cold expanse indifferent to life, it is life, endlessly reshaping itself, remembering through the very matter that composes it. In the quiet pulse of blood, in the shimmer of thought, in the fragile warmth of existence, the cosmos keeps its oldest promise that nothing, not even memory, ever truly disappears. There was a time not so long ago when the universe was thought to be eternal, steady and unchanging, a vast celestial clockwork that had always been and would always be. Stars were believed to hang in place like ornaments in a perfect and infinite sky. And time itself, many thought, stretched backward without beginning. It took a small group of dreamers at the start of the 20th century to challenge that ancient comfort, not poets or mystics, but mathematicians and physicists who began to see the heavens as something alive, something that breathed, expanded, and perhaps even remembered its own creation. Their equations, written in chalk and silence, would transform not only science, but the way humankind understood its place in existence. And what is most remarkable is that behind those calculations lay something very human: faith, curiosity, and a quiet wonder that numbers alone could never explain. In 1915, Albert Einstein published his general theory of relativity, a work so profound that it reshaped the foundation of physics itself. His equations described gravity not as an invisible force pulling objects together, as Isaac Newton had imagined centuries earlier, but as the curvature of space and time caused by mass and energy. In Einstein's universe, space was not a stage on which the cosmos acted. It was part of the action itself, bending and stretching in response to the matter it contained. But even Einstein, cautious of what his mathematics implied, could not at first accept the possibility that the universe might be changing. His own equations suggested that space should either be expanding or contracting. Yet he resisted the idea, adding what he called a cosmological constant to keep the universe still. Later he would call that addition the greatest blunder of his career, though it came from a deeply human impulse, desire for stability in a universe that seemed to demand motion. While Einstein sought balance, others dared to let the equations move freely. In the 1920s, a Russian physicist named Alexander Friedman used Einstein's own formulas to show that an expanding universe was not only possible, but inevitable. By removing the cosmological constant, he demonstrated that if one traced the expansion backward, all galaxies and matter would converge to a single, infinitely dense point, a beginning. His work was first met with skepticism, even dismissal, but the mathematics held. The universe, it seemed, could not have existed forever. It must have been born. Around the same time, in Belgium, another mind was working on the same mystery, a man whose life bridged the worlds of science and faith. Georges Lemaître was a Catholic priest, a mathematician, and an astronomer. trained both in theology and in the physics of Einstein. He saw no contradiction between the two. To him, the act of understanding creation was a way of honoring it. In 1931, he proposed a theory he called the hypothesis of the primeval atom. He imagined that all matter and energy in the universe were once contained within a single, tiny point, a cosmic egg, as he described it, that exploded and expanded, giving birth to space, time, and everything that followed. His words were not poetry, yet they carried the cadence of it. The beginning of the world happened a little before the beginning of space and time, he wrote, suggesting that creation was not an event in time, but the creation of time itself. When Lemaitre presented his ideas to Einstein, the older physicist reportedly shook his head and said, "Your calculations are correct, but your physics is abominable." It was not that Einstein doubted the math. He simply could not yet believe that the cosmos had a beginning. The thought of a universe emerging from nothing seemed too strange, too close to the language of theology. But Lemaitre persisted, refining his model, publishing papers that linked his theory to the redshifts observed by astronomers like Edwin Hubble, who in 1929 confirmed that galaxies were indeed moving away from one another. Slowly, the pieces fell into place. The universe was expanding, and therefore it must once have been smaller. Lemaitre's primeval atom, what would later be called the Big Bang, was no longer just a dream, but the most plausible story of how everything began. There is a gentle irony in all this, that one of the most radical ideas in modern science was born in the mind of a priest. Lemaitre himself never saw conflict between faith and physics. He once said the doctrine of creation never taught that the universe began in time. It teaches that it depends on God. To him, discovering the mechanics of creation did not diminish its mystery. It deepened it. He saw the laws of nature not as divine commands written in stone, but as the unfolding of something sacred and rational, an order that could be described yet never fully possessed. His belief did not interfere with his science. It gave it a kind of humility. He did not seek to prove the divine through mathematics, only to trace the shape of what the divine might have allowed to happen. In the decades that followed, Lemaitre's idea was tested, doubted, and finally vindicated. The discovery of cosmic microwave background radiation in 1964 provided the first tangible evidence of a hot, dense beginning, exactly as his theory had predicted. Even Einstein, before his death, came to acknowledge that the universe was indeed expanding, admitting to Lemaitre, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened." The mathematician's dream, born from equations and quiet faith, had become the foundation of modern cosmology. To think of it now is to see a kind of poetry hidden in the numbers. The story of the universe, once told by mystics and mythmakers, had found its echo in mathematics. What Lemaitre and his contemporaries discovered was not only that the cosmos has a beginning, but that understanding it requires more than intellect. It requires awe. The same awe that once filled temples now fills observatories, and the same wonder that guided prayer now guides calculation. Perhaps that is the truest irony of all, that science, in its deepest form, is not the opposite of faith, but its continuation. The same yearning expressed in a new language, written not in scripture, but in the quiet elegance of equations that describe how light, matter, and time all came to be in the deep future. So distant that numbers begin to lose their meaning, the universe will fall quiet again. The light that once filled its vast spaces will fade. The stars that gave warmth to the darkness will exhaust their fuel. The galaxies will drift apart until even their faintest edges disappear beyond sight. It is an ending not of fire or collision, but of slow, unrelenting distance, a kind of cosmic sigh. The expansion that began with the first great flash of the Big Bang will not stop. It will continue forever, carrying everything farther and farther away until the very concept of togetherness no longer applies. In that future, there will be no nights or days, no horizons of light, only a cold that grows without limit, spreading through the fabric of existence like a silence no sound can disturb. Scientists call this vision the heat death of the universe. But the name is misleading, for it is not heat that will dominate, but the absence of it. It arises from the laws of thermodynamics, which govern the flow of energy, and from the principle of entropy, the measure of disorder in a system. Over time, energy spreads out, differences even out, and the ability to do work, to create motion or life, fades away. Entropy always increases, not out of cruelty, but out of balance. And in the farthest reaches of time, it will reach its final equilibrium. The stars, born in clouds of hydrogen, will burn through their supply of fuel, some collapsing into white dwarfs, others into neutron stars or black holes, and still others exploding into brief supernovas before dissolving into dust. As the ages pass, even those remnants will cool, their light fading until they glow only faintly in the infrared, then not at all. The universe will be filled not with radiance but with memory, traces of what once was. Galaxies that now shimmer in clusters slowly drift apart as the expansion of space accelerates, driven by the mysterious force called dark energy. In a few 100 billion years, distant galaxies will move so far from one another that their light will never reach across the widening void. From any given point in space, the rest of the cosmos will vanish from view. Astronomers of that unimaginable future, if any still exist, will look out and see only their own galaxy, surrounded by darkness, unaware that others had ever been. The history of the universe will be erased from sight, not by destruction, but by separation. The night sky, which today holds billions of stars, will become an empty stage. In this lonely epoch, black holes will remain, the last monuments of gravity's strength. They will roam the darkness, swallowing the remnants of matter that still wander near them. For trillions of years they will persist, the universe's final engines, till even they begin to fade through the slow emission of Hawking radiation. One by one, they will dissolve into faint flickers of light, releasing their mass into space as they evaporate. It will take longer than any number we can meaningfully imagine, a time so vast it stretches beyond all human comprehension. When the last black hole evaporates, when the last particle decays into nothing but low-energy radiation, the universe will enter its final state perfectly even, perfectly cold, perfectly still. What follows such an ending is a question science cannot answer, only approach with imagination. Some physicists believe that this heat death is final, that time will continue, but change will cease, leaving behind a featureless expanse of dark energy and cold photons. Others wonder if this ending might be a prelude, if beneath the ashes of this exhausted cosmos lies the potential for another beginning. In certain models of quantum cosmology, tiny fluctuations in the vacuum, the same kind of tremors that may have birthed our own universe, could still occur. Even in a state of apparent emptiness, space is not truly still. It hums with invisible energy. Somewhere, sometime, far beyond any horizon we can know, a new bubble of existence might form, expanding outward with its own laws of physics, its own version of space and time. To us, it would seem like nothingness, giving birth to something once more, as if creation itself could never stop dreaming. It is difficult to picture such scales of time. It's harder still to imagine the meaning of them. If the future truly ends in silence, what does that say about the noise and light of the present? The stars we see tonight will still be shining for millions or billions of years, and yet their eventual fading feels inevitable, like the cooling of a great fire after its brightest flame. And still, there is something tender in this cosmic mortality. The same laws that will one day bring about the universe's stillness are the ones that made it beautiful, that allowed stars to form, galaxies to swirl, and life to open its eyes. Entropy may lead to emptiness, but without it, there could never have been motion, or growth, or the fragile balance that allows us to exist long enough to wonder about the end in the far future. Perhaps no minds will remain to witness it, yet the universe will continue its silent unfolding, stretching toward infinity. Space will thin until there is no more structure to unravel. Time will lose its meaning, and the last traces of heat will spread so evenly that nothing new can happen. But even then, one cannot help but wonder if the cosmos has ended before, might it not begin again? Could our universe be only one in a series of breaths, Each expansion and collapse a heartbeat of something larger than time itself? Maybe, deep within that final cold, there lingers the faintest echo of warmth, a spark that waits patiently as it did before, for the next universe to rise from the ashes of the old, not as a continuation, but as a memory reborn. And when that happens, as it perhaps always has and always will, light will once again find its way into the darkness, and time will begin to move. There is a clock that does not measure the hours of a day or the seasons of a year. A clock that has no hands in the usual sense and no place in any room. Yet it has ticked in the human imagination since the middle of the 20th century. It is called the doomsday clock. And it does not count down to dawn or dusk, but to the end, to the imagined midnight of human civilization. Created in 1947 by the Bulletin of the Atomic Scientists, a group that included some of the same minds who had worked on the Manhattan Project. It was born from a fear that science, for all its brilliance, had placed in human hands a power too great to control. The first atomic bombs had fallen only 2 years earlier on Hiroshima and Nagasaki, turning entire cities into silence. And those who understood the science behind such weapons began to see that the same curiosity that once sought knowledge now carried within it the seed of annihilation. They needed a symbol, something that could speak to both reason and conscience, and so they made a clock that did not tell time, but emotion. When the first issue of the Bulletin appeared with that image on its cover, the clock set at 7 minutes to midnight. It was a quiet act of warning, not to governments alone, but to humanity itself. Each movement of its hands since then has reflected not seconds but states of mind, hope or fear, cooperation or conflict, wisdom or arrogance. The closer it moves toward midnight, the closer the world seems to disaster. Over the decades, this clock has become both a mirror and a measure of how humanity perceives itself. Hovering somewhere between science and symbolism, between what is and what might be, it has no gears, no pendulum, no mechanism beyond human judgment, yet it ticks louder in the mind than any real machine. In the early years, its movement followed the rhythm of nuclear politics. In 1953, after both the United States and the Soviet Union tested hydrogen bombs, each thousands of times more powerful than the weapons dropped on Japan, the bulletins, scientists moved the clock to 2 minutes to midnight, the closest it had yet come to the symbolic end. That same year, President Dwight D. Eisenhower spoke of the atoms for peace, an effort to turn nuclear power toward creation rather than destruction, but the shadow of that new weapon never lifted. As the decades unfolded, the clock became a kind of diary of human anxiety. It retreated to 12 minutes during the brief optimism of the 1960s. After arms control treaties and scientific collaboration, then crept forward again with each new war, each failure of diplomacy, each revelation that progress and peril are always bound together. The clock's face has changed little, but its meaning has deepened. Over time, the scientists who adjust it have expanded their concerns beyond bombs. They have come to see that humanity's ability to destroy itself does not depend solely on weapons. In recent decades, they have added climate change, artificial intelligence, and biotechnology to the list of threats. Recognizing that the same ingenuity that created medicine and electricity could also unravel the systems that sustain life. When they gather to move the hands, they do not simply calculate risks and equations. They weigh moral choices. The clock is a reminder that the greatest danger does not come from physics, but from the human heart, from pride, fear, and the endless race to outpace one another. What makes the doomsday clock powerful is not its accuracy, but its emotion. It is not meant to predict the end of the world, but to express how near we seem to bringing it upon ourselves. It takes a measurement that belongs to machines, time, and turns it into something painfully human. When the clock was set to 90 seconds to midnight in 2023, the closest it has ever been. The reason was not just the war in Ukraine or the expansion of nuclear arsenals, but the growing sense that global cooperation itself was unraveling. In a way, the clock records not time but trust, and the shrinking of both feels much the same. Each movement of the hand is an act of collective self-reflection, a way for humanity to see its own reflection in the glass of a dial that does not truly exist. There is something almost poetic in this attempt to measure fear through the language of science. The scientists who maintain the clock publish their statements in the sober tone of reason, citing data and probabilities. Yet beneath the surface lies something far more human, a plea. It is a kind of prayer in mechanical form, a hope that by quantifying dread, we might learn to manage it. For all its precision, the clock is ultimately a metaphor for conscience. It reminds us that time itself is not the enemy. What we do within it is. Each minute gained or lost depends not on the spinning of Earth, but on the choices of its inhabitants, decisions made in laboratories, parliaments, and battlefields. The ticking of this symbolic clock is really the sound of those choices accumulating. And yet, amid the unease it evokes, there is also resilience. The clock has never struck midnight. For all the fear and folly of the modern age, humanity has again and again stepped back from the edge, negotiated treaties, dismantled missiles, reduced arsenals, restored dialogue. Each time, the hands have been turned backward, if only slightly, as if to say that awareness itself can be a kind of redemption. It is not time that saves us, but the act of noticing time, of understanding that the seconds we have are shared and finite, in a sense. The doomsday clock is not just a symbol of threat, but of continuity. A reminder that even as the world trembles under its own inventions, it still finds ways to endure. It stands at the intersection of science and faith, calculation and conscience, holding a mirror up to the species that built it. It tells us that time will keep moving whether we listen or not, and that what matters most is not how close we stand to midnight, but whether we remember that we are the ones holding the hands. Somewhere between the tick and the talk of that invisible clock, between the fear that built it and the hope that sustains it, humanity continues to live, measuring not just time, but the fragile distance between knowledge and wisdom, and between survival and the silence that might follow in a small room. Under the slow pulse of night, a clock sits on a bedside table. Its ticking is soft, nearly hidden beneath the rhythm of a sleeping person's breath. The hands move steadily, tracing circles through the darkness, measuring moments that feel both endless and fragile. Outside, the world follows its own unseen patterns, the earth turning through space, the moon climbing and falling, the stars appearing and vanishing behind drifting clouds. Yet in that room where only one person lies between waking and dreaming, time feels like something different, not a law of nature, but a quiet agreement, a way of understanding change. The clock insists that minutes pass, but the sleeper does not notice. In dreams, an hour can stretch to a lifetime or vanish entirely, and no one questions it. When morning comes, the clock will say, "Time has moved forward." Yet the sleeper may feel as though they have returned from somewhere both ancient and weightless, a place where time never learned how to keep count. Scientists have spent centuries trying to capture the meaning of time. Yet the closer they come, the more it seems to dissolve between their fingers. Einstein once showed that time is not a constant river, but a landscape that bends, stretches, and slows, depending on where you stand and how you move. Clocks tick faster on mountains than they do at sea level, and astronauts age more slowly than the people who stay behind on Earth. Every measurement, no matter how precise, reveals that time is not the same for all observers. It is elastic, personal, almost alive. And yet, we continue to live by it, to build our lives around hours and calendars, to name our beginnings and endings by numbers that may not exist outside of perception. If the universe truly has no preferred rhythm, then perhaps time, as we know it, is only the echo of our motion, the mark left by change. Even in the smallest actions of life, we see this illusion take shape. A candle burns and shortens, and we call that the passing of time. But what really happens is the rearrangement of matter, wax into smoke, flame into warmth. A child grows, an old photograph fades, a season ends. But each of these is a story of change, not of an invisible force pushing us forward. Time may simply be the name we give to transformation, to the endless exchange of what is for what will be. In that sense, time is not something that passes through us. It is something we create by noticing difference, the way a shadow lengthens, the way light shifts on a wall, the way we age while trying to remember who we used to be. Memory, too, is what gives time its shape. Without it, every moment would stand alone, unconnected, a series of isolated flashes with no direction. When we recall a childhood smell or the sound of rain on a certain roof, we are not traveling backward in time, but stitching together fragments of change into a pattern that makes sense to us. The human mind cannot live in the present alone. It needs the illusion of before and after to understand its own continuity. Perhaps this is why dreams, which float free from that structure, feel both timeless and strange. They happen somewhere outside the clock's authority, where moments fold and stretch like cloth. The brain does not measure them. It drifts through them. In that way, every dreamer becomes a traveler in a world where time has been set aside. When the first mechanical clocks appeared in the 14th century, they changed not only how people measured their days, but how they thought about themselves. Time, once tied to sunlight and seasons, became something that could be divided and sold. Something people could lose, or waste, or save. The clock turned the movement of the earth into a rhythm of obedience. Hours of work, minutes of rest, seconds of impatience. Even now, centuries later, we remain servants to that rhythm, though we built it ourselves. The irony is that while the clock was meant to bring order, it may have made us strangers to the natural flow of existence. We measure our lives by schedules and deadlines. Yet when we step away into a forest, a quiet room, or the company of someone we love, time softens, its edges blur. And we begin to sense what the physicists have been saying all along, that time is not a thing we can touch. Only a habit we have learned to believe in. And yet, belief gives it power. We speak of time as if it were alive. Time flies, time heals, time runs out, and in doing so, we give it a body it may never have had. The ticking clock becomes a reminder not of reality, but of mortality, of our awareness that change will one day reach even us. But if time is only motion, only the shifting of atoms and memory, then what is it that we fear when we say we are running out of it? Perhaps we are not running out of time at all, but of moments we notice, of changes we can still witness. Perhaps what fades is not time, but our place within it, our chance to be part of the transformation that gives it meaning. Back in the small room, the clock continues its quiet work, indifferent to these questions. The sleeper stirs. The minute hand moves forward, and another day prepares to begin. Outside, the horizon brightens faintly with the color of dawn. In that fragile space between darkness and light, there is no clear boundary between what was and what will be. Only motion, only change. The hands of the clock will keep turning whether anyone watches or not. And still the question will linger, soft and unanswered. If time is not real, if it is only the shadow of movement and memory, then what exactly are we running out of?